Water is so familiar that it almost disappears from notice. It waits in glasses, clouds, rivers, pipes, cells. It cools engines, softens landscapes, carries heat, dissolves minerals, shapes weather, and quietly makes life possible. It is the first substance most people learn the name of, and often the last one they think to question. And yet, beneath that familiarity, water refuses to behave like it should. Its solid form floats instead of sinking. Its liquid form holds heat far more stubbornly than similar substances. Its molecules cling, align, rearrange, and cooperate in ways that resist simple explanation. Even after centuries of careful measurement, precise experiments, and powerful simulations, water still occupies an unusual position in science. Not unknown, not mysterious in a dramatic sense, but incomplete. This is a substance that has been examined by generations of chemists, physicists, biologists, and planetary scientists. It has been measured, modelled, frozen, boiled, compressed, stretched, illuminated, and simulated in extraordinary detail. And still, at its most fundamental level, liquid water remains one of the hardest everyday materials to fully describe. That tension is what this video explores. Not water as a symbol or a metaphor or a miracle, but water as a real physical system shaped by simple rules that somehow give rise to unexpectedly rich behavior. A substance that helped science learn how to measure the world, and that continues to remind science of its limits. So as this video unfolds, it moves slowly from what is firmly known into what is still being debated, from structure to behavior, from molecules to planets, from certainty to open questions. There is no rush to resolve anything here, only an invitation to notice how something so ordinary can remain so deeply unfinished. Welcome to The Sleepy Scientist. If you enjoy calm, thoughtful science like this, consider liking the video and subscribing to the channel. And if you're listening or watching right now, feel free to share where you're joining from, whether it's somewhere shaped by oceans, rivers, rain, or simply a quiet glass of water nearby. Water entered science quietly, long before laboratories looked like laboratories at all. Before instruments, before standardized units, before glassware and calibrated scales, there was a need to understand matter in a way that could be compared, repeated, and trusted. And water, simply by being everywhere and behaving consistently enough, became one of the first substances through which people learned how to measure the world. In the ancient Mediterranean world, water was treated as one of the classical elements. It was grouped alongside earth, air, and fire, not as a substance with internal structure, but as a basic category of existence. In that view, water did not need explanation in terms of smaller parts. It simply was what it was, wet, flowing, heavy, and naturally seeking its level, useful, familiar, and philosophically complete. That way of thinking was powerful, but it placed limits on curiosity. If water was elemental, there was little reason to ask how it behaved internally, or why its properties were so consistent. Measurement mattered less than meaning. Explanation mattered less than classification. A different approach began to emerge centuries later, particularly within the scientific traditions of the Islamic Golden Age. Scholars working across regions that stretched from Central Asia to the Eastern Mediterranean began to treat water not as a philosophical given, but as a physical substance that could be quantified, compared, and tested. Al-Biruni, writing around the year 1000, carried out careful measurements of density using water as a reference. He compared the mass of equal volumes of different materials by observing how much water they displaced, producing remarkably accurate values by modern standards. This was not abstract philosophy. It was experimental method. Water, in this context, was no longer an element. It was a tool. Ibn Sina, known in the West as Avicenna, approached water from a medical and physical perspective. He described its role in bodily processes, its effects on temperature, and its capacity to dissolve substances. He treated water as something whose properties could be observed, not assumed. Heat transfer, purity, and interaction with other materials became practical questions, not philosophical ones. What mattered in this shift was not that these scholars solved the nature of water. They did not. What mattered was that water became a stable reference point, something reliable enough to build other measurements around. From there, water slowly became an epistemic anchor, a substance against which uncertainty could be reduced. As experimental science developed in early modern Europe, this role expanded. When thermometers were first constructed, water played a central part. Temperature scales were defined using water's phase changes. The freezing point and boiling point of water under standard atmospheric pressure became fixed reference markers. These were not chosen because water was special in a cosmic sense, but because it was accessible, repeatable, and behaved predictably enough to be useful. Purity, too, was often judged relative to water. Distillation techniques were refined to produce cleaner and cleaner samples of it. The ability to remove dissolved salts and impurities turned water into a test case for separation methods. If a laboratory could produce pure water, it could likely purify other substances as well. Mass standards followed a similar path. Early definitions of units such as the gram were tied to the mass of a specific volume of water at a specified temperature. Water, once again, was not the object of study. It was the ruler. This quiet role shaped scientific practice in ways that are easy to overlook. Water trained science to expect repeatability. It encouraged the idea that nature could be standardized, that a measurement made in one place could be trusted elsewhere, provided the same reference substance was used. Even as chemistry matured and the classical elements were discarded, water retained its central position. When Antoine Lavoisier helped establish modern chemical nomenclature in the late 1700s, water was no longer considered elemental. It was recognized as a compound. Hydrogen and oxygen combined in a fixed ratio. That discovery was transformative, but it did not demote water's status. If anything, it strengthened it. Water became proof that complex behavior could arise from simple composition. Two lightweight gases forming a stable liquid that flowed, froze, boiled, dissolved salts, and supported life. Yet even then, water's internal complexity was underestimated. Early atomic theory treated molecules as rigid objects. Bonds were fixed, structures were stable. Water fit neatly into diagrams and equations. What science did not yet appreciate was that liquid water is not a collection of isolated molecules. It is a constantly shifting network. Bonds stretch, bend, break, and reform on timescales far shorter than human perception. Order appears and disappears. Structure exists, but only briefly. Ironically, water's usefulness as a reference delayed recognition of its deeper complexity. Because it worked so well as a standard, it was easy to assume it was well understood. The assumption lingered quietly in the background of scientific progress. Throughout the 19th century, water continued to anchor new techniques. Calorimetry, the measurement of heat, relied heavily on water because of its unusually high capacity to absorb energy without large temperature changes. Once again, water was chosen not for mystery, but for stability. In laboratories, reactions were heated and cooled in water baths. Samples were stored, diluted and transported in aqueous solutions. Biological research depended on water to keep tissues viable. Geological studies used water flow to model erosion and sediment transport. In all these cases, water was the medium, the backdrop, the assumed constant, and that assumption shaped habits of thought. Scientific methods grew around water's apparent reliability. Instruments were calibrated using it. Procedures was designed with its properties in mind. The expectation formed that liquids, in general, could be treated similarly, that their behavior could be averaged, smoothed, and simplified. Only later did it become clear that water is a poor representative of liquids as a category. Many of its most useful properties are precisely what make it unusual. Its density anomaly, where the solid form is less dense than the liquid, is rare. Its surface tension is unusually high. Its heat capacity exceeds that of most comparable substances. Its ability to dissolve ionic and polar compounds is exceptional. These traits were known individually, but their deeper origin was not pursued with urgency. After all, water worked. What emerges, looking back, is a subtle irony. Water helped science learn how to measure, standardize, and control the physical world. It trained generations of researchers to trust experimental consistency. It anchored definitions of temperature, mass, and purity. It made laboratories possible in their modern form. At the same time, that very familiarity masked unresolved questions. Water became the substance through which science learned confidence, even as it quietly resisted complete description. This is not a story of ignorance. It is a story of success creating blind spots. Water did not just shape theories about matter, it shaped scientific behavior itself. It influenced what counted as a good experiment, what counted as reliable data, and what kinds of complexity were worth confronting. Only much later did researchers begin to realize that the substance they trusted most might be the one that challenged their assumptions most deeply, and that realization did not arrive as a dramatic discovery. It arrived slowly, through inconsistencies, anomalies, and models that worked almost perfectly, but not quite. Water had done its job too well. It taught science how to measure the world before science was fully prepared to measure water itself. At first glance, water looks like the easiest possible problem. Two hydrogen atoms, one oxygen atom joined together in a small, tidy arrangement. No long chains, no branching structures, no exotic elements. Compared to the sprawling molecules of biology or the complex lattices of solid materials, water seems almost modest. It appears to be the kind of system that should give up its secrets quickly. For a long time, scientists expected exactly that. In classical chemistry, molecules were imagined as small mechanical objects. Atoms were treated like beads connected by stiff links. If the parts were known, the behavior should follow. This way of thinking worked surprisingly well for many substances, especially gases, where interactions are weak and brief. It also worked well enough for solids, where atoms vibrate around fixed positions. Water, however, began to resist that simplicity as soon as scientists tried to describe it at the atomic scale. In the early 20th century, chemistry and physics were undergoing a quiet revolution. Classical ideas about atoms and bonds were giving way to quantum mechanics, a framework that replaced certainty with probability and rigid trajectories with wave-like behavior. Chemical bonds were no longer just connections. They were shared states, governed by the mathematics of quantum theory. Among the scientists shaping this shift were Walter Heitler and Fritz London. In the year 1927, they published work explaining the chemical bond using quantum mechanics, showing how electrons could be shared between atoms in a stable configuration. Their ideas laid the foundation for modern molecular theory. Water was one of the simplest test cases for this new understanding, and yet even here complications appeared immediately. The bond between oxygen and hydrogen is not evenly shared. Oxygen pulls more strongly on the electrons, creating an uneven distribution of electrical charge. This asymmetry gives the water molecule a permanent polarity. One side is slightly negative, the other slightly positive. At the level of a single molecule, this seems manageable. Polarity can be measured. Bond angles can be calculated. Energies can be estimated. Quantum chemistry handles this part of the problem well. The difficulty begins when molecules stop being alone. A glass of water does not contain a handful of molecules. It contains on the order of 10 sextillion molecules. That is a 1 followed by 22 zeros. Each of those molecules interacts with its neighbours through electrostatic attraction, repulsion, and short-range quantum effects. None of these interactions is especially strong, but there are so many of them that they dominate the behaviour of the liquid. This is where classical intuition begins to fail. In simple systems, understanding the parts often leads directly to understanding the whole. Double the number of molecules, and many properties double as well. Add more energy, and temperature rises in a predictable way. These linear relationships are comfortable. They scale cleanly. Water does not. Small changes at the molecular level can produce large nonlinear effects at the macroscopic level. Cooling water slightly can make it expand rather than contract. Adding heat does not raise its temperature as efficiently as it does for other liquids. Freezing rearranges molecules into an open structure rather than a compact one. These behaviors do not arise from individual molecules. They arise from coordination. Physicists refer to this as a many-body problem, a situation where the behavior of a system cannot be reduced to the sum of its parts, because the interactions between those parts matter as much as the parts themselves. In a two-body problem, such as a planet orbiting a star, equations can be written down and solved exactly. In a three-body problem, the solutions become unstable and sensitive to initial conditions. With many bodies, exact solutions vanish entirely. Patterns emerge, but they must be described statistically rather than precisely. Liquid water is a many-body system of staggering complexity. Each molecule forms temporary associations with several neighbours through hydrogen bonding. These bonds are weak compared to covalent bonds, but they are directional and cooperative. When one bond forms, it influences the likelihood of others forming nearby. Networks appear, dissolve, and reappear on timescales of trillionths of a second. At any given moment, the liquid contains regions that resemble ice, regions that resemble disordered fluid, and everything in between. These regions are small and short-lived, but they matter. They influence density, viscosity, heat capacity, and the way sound and light move through the liquid. From a distance, water looks smooth and uniform. At the molecular level, it is restless. This restlessness is not noise, it is structure in motion. Quantum chemistry can describe the interactions between a few molecules with impressive accuracy. Statistical mechanics can describe average behavior across many molecules. The challenge lies in the bridge between them, the point where individual quantum interactions give rise to collective classical properties. This is why simplicity at the molecular level does not guarantee simplicity at larger scales. The rules do not disappear, they multiply. An individual water molecule behaves one way in isolation. Place it in a cluster, and its electronic environment changes. Place it in a dense liquid, and its identity becomes inseparable from its surroundings. Properties that belong to the molecule alone give way to properties that belong to the network. In this sense, liquid water is not an object, it is a process. This perspective represents a shift in how scientists think about matter. Instead of asking what a molecule is, the question becomes how molecules coordinate, how patterns arise from interaction rather than instruction, how order emerges without design. Water was among the first substances to force this realization. It behaved too strangely to be explained by treating molecules as independent actors. It demanded attention to correlation, fluctuation, and collective motion. There is a quiet lesson here. Nature does not promise that small causes lead to small effects. It does not guarantee that understanding the pieces will automatically explain the whole. Water, despite its apparent simplicity, demonstrates this gently but persistently. 2 hydrogen atoms and 1 oxygen atom are enough to build a system that resists tidy explanation, not because it is exotic, but because it is deeply interconnected. This is not a failure of science. It is a boundary condition, a reminder that prediction becomes harder as cooperation increases. Water is simple only until it touches itself. Water's unevenness begins at the smallest scale, but it does not stay there. A single water molecule carries an internal imbalance. Oxygen pulls more strongly on shared electrons than hydrogen does, leaving one side of the molecule slightly negative and the other slightly positive. This is not a full charge, like that of an ion, but a partial one. The molecule becomes a dipole, with a built-in orientation and direction. On its own, that detail might seem minor. Many molecules have uneven charge distributions. What makes water distinctive is how strongly those dipoles influence one another when many molecules are brought together. In liquid water, every molecule is surrounded by others that are also unevenly charged. Each dipole feels the presence of its neighbours. They rotate, shift, and reorient in response, constantly adjusting to local electric fields created by nearby molecules. This collective sensitivity gives rise to one of water's most important properties, its dielectric behaviour. Dielectric behaviour describes how a material responds to electric fields. In simple terms, it measures how well a substance can reduce, or screen, electrical forces between charged particles. Water is exceptionally good at this. Its dielectric constant is high compared to most liquids, meaning that electric charges immersed in water feel each other far less strongly than they would in air or vacuum. This screening effect is not passive, it emerges from motion. When a charged particle enters water, surrounding molecules rotate so that their oppositely charged ends face it. This reorientation partially cancels the particle's electric field. The charge becomes wrapped in a responsive cloud of aligned dipoles. The field still exists, but it is softened, spread out, and moderated. This behaviour was explored in depth by Lars Onsager in the mid-20th century. Onsager developed theoretical descriptions of dipoles in polar liquids, showing how long-range interactions arise not just from individual charges, but from the collective response of many molecules acting together. His work helped clarify why water cannot be treated as an inert background. Its molecules actively rearrange themselves in response to their environment. The consequence of this is subtle but profound. Water does not merely host chemical reactions, it reshapes the forces that drive them. Ions dissolve in water because the liquid stabilizes separated charges. Positive and negative ions are pulled apart not by magic, but by the energetic benefit of being surrounded by oppositely oriented dipoles. The screening effect lowers the energy cost of separation, making dissolution favourable. Acids and bases behave differently in water for the same reason. Protons do not wander freely. They move through a constantly shifting network of hydrogen bonds, hopping from molecule to molecule in a process known as proton transfer. Water participates directly, rearranging itself to enable motion. Even neutral molecules are affected. Polar compounds dissolve readily because their charge distributions align with those of surrounding water molecules. Nonpolar substances struggle because they disrupt the local dipole organization without offering compatible interactions in return. In this way, water acts less like a container and more like a collaborator. This idea represents a departure from earlier chemical thinking. In classical reaction schemes, solvents were often treated as background conditions. They provided space, temperature control and mixing, but did not fundamentally alter reaction pathways. Water resists this simplification. Its polarity means that every reaction occurring within it is embedded in a responsive electrical environment. Forces are screened, amplified, redirected, and reshaped by the surrounding liquid. Energy landscapes change, transition states shift, reaction rates adjust. The medium becomes part of the mechanism. This responsiveness extends beyond chemistry into larger-scale organization. Because water's dipoles interact over relatively long distances, patterns of alignment can propagate through the liquid. These patterns are fleeting, but they influence bulk properties such as viscosity, surface tension, and the way water responds to external fields. Onsager's work emphasized that long-range order does not require rigid structure. Correlations can exist without permanence. Molecules do not need to lock into place to influence one another. Statistical alignment is enough. This is why water behaves coherently without becoming solid. At any moment, regions of the liquid exhibit partial alignment of dipoles. These regions form and dissolve continuously. They are shaped by temperature, pressure, dissolved substances, and nearby surfaces. None of them last long, but together they give water its characteristic behavior. The result is a liquid that senses and responds. Introduce salt, and water reorganizes to stabilize ions. Introduce heat, and molecular motion disrupts alignment. Introduce an electric field, and dipoles rotate collectively. Introduce a surface, and nearby molecules adopt preferred orientations. Water is not indifferent, it reacts. This sensitivity allows water to support complex systems. Biological molecules rely on it to moderate forces that would otherwise tear structures apart. Charge groups on proteins remain stable because water softens their interactions. Membranes form because water reorganizes itself around nonpolar regions, effectively pushing them together. None of this requires intention or design. It arises from polarity interacting with density and motion. What makes this remarkable is that the same underlying property explains phenomena across scales. The uneven charge distribution of a single molecule influences the behavior of oceans and cells alike. It shapes how clouds form, how minerals dissolve, how nerve signals propagate, and how enzymes function. The link between microscopic polarity and macroscopic order is not linear. Small changes in alignment can lead to large shifts in behavior. Temperature, for example, affects how easily dipoles can reorient. As thermal motion increases, alignment becomes harder to maintain. Dielectric screening weakens slightly. Reaction rates change. These effects are measurable. They are predictable in broad terms, yet they remain difficult to calculate precisely because they depend on collective motion rather than fixed structure. Water, in this sense, behaves more like a responsive fabric than a static material. It stretches, relaxes, and redistributes forces dynamically. It does not simply transmit interactions, it modifies them. This is why treating water as a passive background leads to misunderstanding. It is not a neutral stage on which chemistry unfolds. It is an active participant that shapes what is possible. The uneven balance within each molecule scales upward into an uneven balance across the entire liquid. Order and disorder coexist. Stability emerges from motion. Screening arises from responsiveness. Polarity does not just explain why water dissolves salts or conducts electricity weakly. It explains why water organizes systems without rigid structure, why it supports complexity without freezing into place. Water's charge imbalance never resolves. It persists, fluctuates, and propagates. And in doing so, it turns a simple molecule into a medium capable of shaping entire systems. The imbalance is not a flaw. It is the source of water's quiet influence, and once noticed, it becomes impossible to ignore. The strange power of water does not come from strength. It comes from cooperation. At the heart of that cooperation lies a subtle interaction known as hydrogen bonding. It is weaker than the bonds that hold atoms together within a molecule, yet far more influential than its modest strength would suggest. Hydrogen bonds are temporary directional attractions between slightly charged regions of neighboring molecules. In water, they appear everywhere, all the time. Each water molecule is capable of forming several hydrogen bonds at once. The positively charged hydrogen atoms are attracted to the negatively charged oxygen atoms of nearby molecules. These attractions pull molecules into loose associations, forming local groupings that resemble structure without ever settling into permanence. Early attempts to understand this behavior focused on individual bonds. Linus Pauling helped clarify how hydrogen bonds arise from electronic structure and why they favor specific orientations. His work established hydrogen bonding as a real, measurable interaction rather than a vague attraction. That alone was a major advance. But it soon became clear that knowing how a single hydrogen bond behaves does not explain what happens when trillions of them interact at once. In the 1930s,